We are equipped with unified data structure, which greatly facilitates the group identification and the group merging operation. Now we can reformulate the problem with the help of the unified. This problem can be considered as a graph partition problem, where we group each node into a list of subsets. Each number in the input list is represented as a node in the graph. The connection between the nodes, which is edge, can be happen if and only if two nodes share a common factor greater than 1. And one naive idea will be that we enumerate all pairs of nodes in order to partition the nodes into groups with the help of the unified data structure, as we just implemented. This would pass some test cases. Since the algorithm has a quadratic time complexity, it would exceed the time limit for more tougher cases. So a more efficient idea would be that we build a group led by each of the common factor of the number. So this can be done in a single iteration over each number. So for each number, we enumerate all factors that divide the number, and then we attribute the number to each group led by factor. For example, we use the union function for number and factor. Essentially, we build a Venn diagram where each subset contains a series of numbers as well as factors. And let's take the input number 6 as our example. It can be divided both by the factors of 2 and 3, and as a result, it can be attributed to the both groups that has the factors respectively. And thanks to the number 6, eventually the groups led by 2 and 3 respectively can be merged together. So at the end, all of the input number can be attributed to a single big group, and thanks to all of the joins among the subgroups. First, let's check number 12 as our example. We iterate the factors from 2 to 3 until 4, because 4 is greater than the square root of the 12. Because 12 modulo 2 is 0, so we try to merge the number 12 with the factor 2, and we also have to merge the number 12 with the complement factor 6. And 12 modulus by 3 is 0, so we try to merge the number 12 with the factor 3. And we also have to merge the 12 with the complement factor 4. So 2 and 3 are factors, and 4 and 6 are complement factors, which is A4 divided by factors. And now let's look at another example, 21, which can modulus by 2, 3, 4, and 5, because 5 is greater than the square root of the 21. 21 modulus 2 is 1, 21 modulus 3 is 0, 21 modulus 4 is 1, so we try to merge the 21 with the factor 3, and we also have to merge the 21 with the complement factor 7. And then, let's check number 39. We modulate with 2, 3, 4, 5, 6 until 7, because 7 is greater than the square root of 39, so we stop before 7, and we get the result, which is 1, 0, 3, 4, 3. And only the modulo 3 get a result 0. So we try to merge the 39 with the factor 3, and we also merge the number 39 with the complement factor 13. The first step, we attribute each number to a series of groups that are led by each of its factor, and we iterate through each number denoted as num, and for each number, we iterate from 2 to the square root of number to find out all of the factors. For each factor of num, we just union the num and the factor just by merging the groups that possess the element nums and factor respectively. And in addition, we union the num and the num floor divided by factor just by performing the same union operation on the complement factor as well. Let's say we have nums, which is 20, 50, 9, 27, 63, and we try to use a for loop for num in nums. We use a find method to find the group ID of the num. So the 20's group ID is 2, and the 50's group ID is also 2. So the group count of 2, which is 0, 1, 2, they have 2 elements. And then let's iterate finish them. We run the find method for 9, which have the group ID 3, and also for 27 and the 63. So the group count of 3 is 1, 2, 3, which is 3. Then finish. After them, we just use a max function to find which one is the biggest, which is 3. The second step, we iterate through each number a second time to find out the final group that the number belongs to. So with the mapping between the number and its group ID, for example, the name is the key, which is pointing to the value group ID. It is intuitive to find out the group that has the most elements. Let's analyze the complexity. Since we just applied the union find data structure in our algorithm, if we have m operation, either union or find are applied to n elements, so the total runtime is O of m multiplied by log of n time, where the log multiply is an iterative algorithm. The log multiply represents the number of times that the logarithmic function needs to be applied before the result is less than or equal to 1. This means that the actual running time of this algorithm is faster than the standard logarithmic time complexity, which is O of log of n. In our case, the number of elements in the union find data structure is equal to the maximum number of the input list, in this case, which is the maximum of the names. We let n be the number of elements in the input list, and let m be the maximum value of the input list. So the number of the factors for a given number is bounded by O of square root of m. Let's assume that any number that is less than square root of m can be divided by m. So we can then have 2 times square root of m pairs of factors. In the first step, we iterate through each number n times because there are n iterations, and for each number, we iterate through all its factors, which is up to 2 times square root of m iterations. So as a result, the time complexity of this step should be O of n multiplied by square root of m multiplied by log of m times. In the second step, we iterate through each number again, but this time, for each iteration, we perform only once the union find operation, hence the time complexity for this step would be O of n multiplied by log of m time. So to sum up, the overall time complexity of this algorithm would be O of n multiplied by square root of m multiplied by log of m plus O of n multiplied by log of m, which is asymptotically equal to O of m multiplied by square root of m multiplied by log of m times. The space complexity of the union find data structure is O of m space, as we need to create a parent list and a size list, which is size m. Well, the m is the maximum value among the number in the input list. In the main algorithm, we use a hash table to keep track of the account for each group. So in the worst case, each number forms an individual group, so therefore the space complexity of this hash table is O of n. So to sum up, the overall space complexity of this algorithm is O of m plus O of n, which is O of m plus n space.